Hello guys, today I'll be explaining the topic 6 nitrogen notes. So I'll explain it and I'll do the questions as well. So let's start. Nitrogen is obtained industrially by the fractional distillation of liquid air. So now we have our first source of nitrogen, which is the fractional distillation of liquid air. It's highly unreactive, so we can say it's inert, and can only be used by plants once nitrogen-fixing bacteria change it into soluble compounds in the soil. So, question 1, how is nitrogen extracted industrially? If we go back, we can see that nitrogen is obtained industrially by the fractional distillation of liquid air. All right? Now, you can write that, or you can go into detail. Meaning that you liquefy the air. How do we liquefy the air? We put a lot of pressure on it. We call this compression. So we do compression on the air and then it liquefies. So after liquefaction, then the liquid air will be passed through the fractionating tower, where it will become distilled, and then we will obtain nitrogen. So the nitrogen will be obtained as a liquid, so you can make it as gas or you can keep it as a liquid. Now part B. Does the process involve primarily physical or chemical changes? Are we changing the composition of liquid air in the process of fractional distillation? No, we're doing physical changes. So we say the process involves physical changes. Number 3, is nitrogen collected pure? I don't think we can get it pure using fractional distillation, because it will have some remains of some of the other things in liquid air. So here our answer would be no. Now, uses of nitrogen in the industrial manufacture of ammonia by the Haber process. So we use nitrogen to make ammonia in the Haber process, and we also make fertilizers of ammonia. So CQD number 2 lists 2 uses of nitrogen. It is for the Haber process to make ammonia, all right, or it is for the making of fertilizer. Now, the Haber process, we're going to discuss the Haber process in detail. Haber process is the industrial manufacture of ammonia gas. What is ammonia? Ammonia is a colorless gas with distinctive odor. All right? No color, but it has a strong odor. It's less dense than air, meaning it will float above the air, and very soluble. So if we put it in an aqueous solution or in a solution, it will dissolve. It's soluble, basically. It's very important. Ammonia is very important to make fertilizers for the plants, and explosives to explode. This is why its production is a very important industrial process. All right? So ammonia is produced by the direct reaction between nitrogen and hydrogen gases. What is ammonia? It is NH3 in a reversible reaction. So we can. Now, how do we make ammonia? It's nitrogen that reacts with hydrogen, and NH2 will give us NH3, and of course it's a reversible reaction. Then to balance it, we'll have to put a 3 here and a 2 here. So this is the balanced equation of nitrogen and hydrogen gases in a reversible reaction. So the raw materials that we need to produce ammonia are nitrogen from the fractional distillation of liquefied air, then hydrogen from methane. So CH4 plus 2H2O gives us CO2 plus 4H2. So again, how do we collect nitrogen? We collect nitrogen from the fractional distillation of liquefied air, and we collect hydrogen from the reaction between methane and water. The reaction between methane and water will give us what? It will give us carbon dioxide and 4H2 gas. Now this is with a catalyst. Here they're telling us ni catalyst, meaning no catalyst. So without a catalyst, it will be CH4 gas plus H2O gas gives us CO gas plus 3H2 gas. Please memorize them, very, very important. Now, of course, there are conditions for the Haber process. Like for any process, there are conditions. The conditions include that the temperature is 450 degrees Celsius. Our pressure, you remember for the sulfur, it was 2 atmospheric pressure. Now it is 200 atmospheres, which is 20,000 kilopascal. Now our catalyst is what? It is finely divided iron Fe. So in this reaction over here, we used our catalyst, which is what? The finely divided iron Fe. In the second reaction over here, they didn't use a catalyst, so we are not using the Fe. So this is what our reaction is going to look like. We have N2 gas plus 3H2 gas will give us 2NH3, and delta H is negative. If delta H is less than 0, we say it is exothermic. So the Haber process is an exothermic reaction with the catalyst being finely divided iron and the conditions of 450 degrees Celsius and 200 atmospheric pressure. Now, being such an important process, the Haber process has been studied over a very wide range on temperature and pressure conditions. So, the Haber process is a very important process, we should know. Now, this is what it will look like. This is what we call, or not what we call, this is the machine that will make the N2 and H2, the nitrogen and hydrogen, into ammonia. So how do we do it? We have N2 coming here. How do we get N2? From the fractional distillation of water, and H2 coming here from the reaction of methane and water. Alright, so then the gases are mixed and scrubbed and they come into this compressor. What happens in the compressor? They get compressed, they get liquefied. In other terms, the compressor will liquefy hydrogen and nitrogen, and then they will continue all the way until here. Here we have beds of our catalyst which will speed up our reaction. So then the N2 and H2 will react, okay? And our conditions are 450 degrees Celsius and 200 atmospheres, okay? And then finally they will go into the cooler and we will produce liquid ammonia. Now, the effect of altering the conditions on the rate of the reaction and the reaction yield. So, if we increase the temperature, we know this is our reaction. It is N2 plus 3H2 gives us 2NH3 plus 92 kilojoules. So they're telling us, if we increase our temperature, according to Le Chatelier's principle, first our imposed change is our increase of temperature of exothermic. According to Le Chatelier's principle, there is a partial counteraction. Okay? Then, this happens by decreasing our temperature of exothermic. And so then, as a result, to decrease its temperature, the products will have to give heat to our reactants. So we say this is a backward reaction, or it shifts to the left. So if we read, increasing the temperature will favor the endothermic reaction, meaning it will give heat to the reactants, so equilibrium will shift to the left. As a result, what happens? There is a lower percentage yield of our products, and the reaction rate will be faster. Why? Because we are giving more heat to our reactants, and if we increase the temperature, then definitely the reaction rate is faster. Now pressure, we have again N2 plus 3H2 gives us 2NH3. Here we have 4 gases, here we have 2 gases. So if we increase the pressure, definitely the one with more gases is going to give to the one with less gases. So our reactants are going to give to our products. Since the reactants are giving to the products, what's happening? It is going to be a forward or right shift. So we can say that increasing the temperature favors the number of lesser gaseous moles, so equilibrium shifts to the right. As a result, there is a higher percentage yield. Since we're shifting to the right, the concentration of the products increases, so there is a higher yield, and there is a higher reaction. Why? Because we are increasing the pressure of our reactants, so then they will definitely have more collisions, more effective collisions, and they will react faster. Now, what's the problem? A high pressure is an expensive procedure, and there might be a high risk of explosion. Definitely, a high pressure is definitely a very high risk of explosion. Now, important notes. During the Haber process, the percentage yield of ammonia is low, only 8%. Okay, very, very low. Although the Haber conditions of temperature are 450 degrees Celsius and 20,000 kilopascal give a low percentage yield, we still use them as a compromise or optimum conditions, meaning these are the best temperature and the best pressure. They will give us enough product at an acceptable rate. They are more than economic, meaning they don't cost us enough money. They don't cost us a lot of money, okay? And we will get a high percentage yield, okay? Even though we're not paying a lot, because if we paid a lot, what will happen? We'll have a higher pressure, which is a very risky case of explosion, and definitely a slower temperature reaction. So these are important notes. Now, number 3. Of course, the catalyst on anything, if we're doing the equilibrium rule, it will not change anything in the concentration, and it will not change anything in the equilibrium. The only thing it will do is attain the reaction rate faster, or it will attain the equilibrium position faster. Now, number 4, reducing the concentration of ammonia. So again, let's write our reaction. We have N2 plus 3H2 will give us equilibrium to NH3. If we decrease the concentration of our products, our imposed change is that product concentration decrease. According to Le Chatelier's principle, there is a partial counteraction. How does this happen? This happens by the total opposite of what our imposed change is, which is increasing the concentration of our products. As a result, for the concentration of our products to increase, it will have to take from our reactants, so the reactants will give concentration to our products. So then we can say that our concentration of reactants will decrease, whereas the concentration of our products will increase. Let's read what they said. They said ammonia has a much higher boiling point than nitrogen and hydrogen, so it can be easily removed from the reaction mixture by cooling. When the percentage of ammonia in it reaches around 15%, the cooling will condense the ammonia into a liquid, leaving hydrogen and nitrogen gases which get recycled. This will pull the equilibrium system toward producing more ammonia. So out of this, they got what? If you reduce the concentration of ammonia, then you will end up producing more ammonia to replace the removed ammonia, to maintain what? To maintain our equilibrium. So by recycling, the yield can be increased to about 98%. That's a really big amount compared to what was here, 8%. So that was for 4. Now, ammonia is stored under pressure as a liquid. Ammonia can be produced in the laboratory when ammonium salts react with bases. Typical examples would be heating ammonium chloride and calcium hydroxide. So this is ammonium chloride solid, and we will heat it with calcium hydroxide solid. It will produce what? It will produce ammonium gas, and it will produce our precipitate, not our precipitate, our solid, which is calcium chloride, calcium dichloride, and a liquid, which is water. All right, so again, if we mix ammonium salts, which is basically ammonium chloride in this case, with calcium hydroxide, we're gonna get ammonium as a gas, then calcium dichloride as a solid, and as our liquid we will get water. So now CQD number 4. Ammonia, NH3, is produced by the Haber process according to the following chemical equation. The graph below shows the percentage of ammonia changes with temperature in mixture at equilibrium. What is meant by the term dynamic equilibrium? We took it. Dynamic equilibrium means that microscopic, to be more specific, 2 microscopic processes are occurring at the same time, okay, in opposite directions, okay, while no changes in macroscopic properties. So dynamic equilibrium means that two microscopic processes are happening at the same time. For example, nitrogen gas and hydrogen gas producing ammonium, and ammonium producing hydrogen and nitrogen gas at the same time, because our products and our reactants will coexist at the same time. And so they will do their reactions at the same time. So we say two microscopic processes occurring at the same time in opposite directions, meaning this is going forward and this is going backward. But there are no changes in macroscopic properties. Macroscopic meaning the visible properties. So how does the percentage of ammonia change with temperature? By looking here, an increase in temperature decreases our percentage of ammonia. So as we can say, increase in temperature decreases concentration of ammonia. So see, on the graph below, sketch the graph that shows what happens to the percentage of ammonia in the equilibrium mixture as the pressure changes. So let's see, we have N2 plus 3H2 gives us 2NH3. Definitely here we have 4 gases and here we have 2 gases. So as we increase the pressure, the 4 gases, the one with the more gases has to give the one with the less gases. So the reactants will be giving to the product. So consequently, the concentration of our products, which is NH3, will increase. So we can say as the pressure increases, our ammonia at equilibrium will increase. Of course, we started with a specific amount. So let's say we're going to start here, around here. Okay, then we increase. And then finally, it will stop. So this is what our graph will look like. Now explain why the graph in part C has this shape. We said we had N2 plus 3H2 equilibrium 3 NH2, or no, my bad, I mixed up, 2 NH3. Okay, now why is it like this? Because here we have 4 gases, here we have 2 gases, and definitely if we increase the pressure, it will favor the one with the less gases. So we will say increase in pressure favors number with less gases. Now, CQD number 5. Answer the following questions regarding the industrial manufacture of ammonia, the Haber process. During the Haber process, only a small percentage of hydrogen and nitrogen gas is converted into ammonia. How are the unreacted gases separated from ammonia? They are separated by what? By cooling. So let's go up and see what they mean exactly. Over here. Here we are producing ammonia. This liquid here is ammonia. So we go down, and not only in this liquid do we have ammonia, but we have NH3 as a gas, not only liquid ammonia, but NH3 as a gas, and N2 and H2 as a gas. So with the cooler, the ammonia will liquefy, and so then the N2 and H2, which need a lot of temperature, a very low temperature to liquefy, they will stay as a gas, and so then they will go up and repeat. So they're asking us, how do we separate nitrogen and hydrogen from ammonia? By cooling. Now what happens to the unreacted nitrogen and hydrogen after it has been separated? It will be reused. So we say it is recycled. Again, we say it is recycled, and our rate increases by 98%. Because if we go up and we see over here, our rate increases to 98%. Now part C. Haber process uses 450 degrees Celsius, resulting in a percentage yield of 15%. Explain. So we have a high amount of heat. Our reaction is what? It is N2 plus 3H2 equilibrium 2 NH3 plus, I think, 92 kilojoules. So if we are gonna increase our temperature, all right, according to first imposed change is temperature exothermic increased, then according to Le Chatelier's principle, there's a partial counteraction. How does this happen? This happens by decreasing the temperature of our exothermic reaction, and then as a result, the concentration of reactants increases, whereas the concentration of products decreases. Why? Because the products are giving heat to our reactants. So since the products are giving to our reactants, we say this is a backward or a left shift. Okay? So definitely, since products are given to reactants, reactants concentration will increase and products concentration will decrease. So our percentage yield becomes less because it will favor the backward reaction because of increased temperature. Now, part D. What is the effect when the temperature is increased in the Haber process on the rate of reaction? If we increase the rate of reaction, if we increase the temperature, the rate of reaction becomes faster. So here it is faster. Then what happens to the position of equilibrium? Like we did before. In the end, we got that our products are gonna give heat to our reactants because it's an exothermic process, okay? And because the products are giving heat to our reactants, then it is a backward or left shift. So we say the position is backward or left shift. So that was part D. Now part E. What is the effect on equilibrium position when the pressure is increased in the Haber process? So I don't know how many times they asked us this question. So what's the Haber process reaction? It is N2 plus 3H2 equilibrium 2NH3. So here we have 4 gases and here we have 2 gases. So definitely the one, if we're increasing the pressure, then the one with the more gases will be giving to the one with the less gases. So the reactants will be giving to our products. And then finally we can say that it is a forward or right shift. So the equilibrium position will shift to the right. Why is that? It is because it will favor an increase. Let's write it like this. An increase in pressure favors number of less gases. So it will move then to the right. CQD number 6. The diagram below shows some reactions of substance X, heat with ammonium compound, heat with dilute acid. What is this substance X? We have substance X. If you heat it with an ammonium compound, you will get ammonia. However, if you heat it with a dilute acid, you will get a salt. So let's go up and check. Over here, look. So when ammonium salts react with our bases, what happens? We get NH3. So if we go down, let's re-understand what they're asking us. They're telling us substance X reacts with an ammonium compound, which is ammonium salt. We will produce ammonia, which is NH3. So substance X is definitely a base. Now, how could we obtain ammonia from ammonium sulfate? So what is ammonium sulfate? Ammonium sulfate is an ammonium compound. And we said if we heat an ammonium compound with a base, we will produce ammonia. So all we need to do is heat ammonium sulfate with a base. Base means an alkali. So yes, a base means alkali. It can mean also alkaline. Now what's the difference between alkali and alkaline? Alkali are substances, or alkali substances are bases which are soluble in an aqueous medium. So definitely anytime we see ammonium sulfate, we see it's an ammonium compound. So we have to heat it with a base, meaning we're going to choose alkali in this case. So let's complete the following reaction. The following reaction is we have NH4Cl. So this is what? This is our nitrogen and 2 compound. Alright, then we're producing NaCl, NH3, H2O. So we have in here 1 nitrogen, 4 hydrogen, 1 Cl, and on this side we have 1 Na, 1 sodium, 1 Cl, 1 nitrogen, 3 hydrogen, and then 2 hydrogen and 1 O. So let's cancel out the ones we already have. We have already 1 N, we have already 1 Cl, we have, if you cross this out and you take 1 from here, so now you have 4 hydrogen and 1 hydrogen is left. And then finally we are left with what? N, A, O, and H. So what's our equation here? What's our chemical here? It is NaOH. Now CQD number 15. Give the chemical equation for the synthesis of ammonia in Haber process. Very easy, we know it. It's N2 plus 3H2 equilibrium sign to NH3. What are the conditions of pressure and temperature needed for optimum yield? How many times are they repeating this? So many times. So we need 200 atmospheres, okay? And our temperature, this is our pressure, and our temperature is 450 degrees Celsius. These are for the optimum yield. Now, give the name of the catalyst used in this process. We said finely shredded or cut iron. So in the Haber process, these are our answers depending on the book. I don't know if they're different in the answers. If they are different in the answers, let me just check. Yes, they're different, but they are pretty much the same. Only in the answers, they're not very specific. Okay, however, we need to be very specific and follow what is written in the book. So now we reached fertilizers. Plants usually obtain what they need to make their food by photosynthesis from the soil and air. However, when the same plot of land is used every year, nutrients in the soil get depleted and need to be replenished by fertilizers. So for the fertilizers to work and to replenish the nutrients in our soil, they need to be water soluble and accessible to plant as they absorb them through their roots. So ammonia is used in the production of fertilizers. Ammonia salts and nitrates are used as artificial fertilizers. So remember, ammonium salts and nitrates are used as artificial fertilizers. The most important of which is ammonium nitrate, which is the principal nitrogenous fertilizer containing 35% by mass nitrogen. So this is our equation. We have ammonia aqueous plus our nitric acid, which is HNO3, will produce for us NH4NO3, which is our fertilizer. So the ammonium nitrate product is dried and spread on our land, this which we call it ammonium nitrate. It's dried and then spread on the land. So fertilizers contain compounds of the three essential elements: nitrogen, protein production, and green foliage. So why do we need nitrogen? They produce the proteins and they make the plant green. Potassium, it helps the plant and flowers and fruits grow healthier. And phosphorus will give it strong roots. So such fertilizers are known as NPK. N is for nitrogen, P is for phosphorus, and K is for potassium. Now, we don't have all of them. Not everything that contains nitrogen, phosphorus, and potassium are fertilizers. No, they are specific. We have NH4NO3. Remember, it's called ammonium nitrate, NH4NO3, or ammonium phosphate, which is NH4,3PO4. This is examples of nitrogen or nitrogenous fertilizers. Then examples of phosphorus fertilizers are NH4,3PO4, and examples of potassium containing fertilizers include the potassium phosphate, which is K3PO4, or potassium nitrate, which is KNO3. Now, different plants require different proportions of these elements. Definitely not everything is the same, like how not all humans are going to eat the same amount, not all plants are going to require all the same amounts. So, importance of fertilizers. Why do we need fertilizers? They increase the rate of plant growth, so plant growth increases, and a higher yield for crops, so a higher crop or food yield. Now, issues with fertilizer. If we have too much fertilizer, okay, the rain will wash the fertilizer off the land and into the river streams. This is pollution, a type of water pollution. This leaching leads to the growth of algae. Oh, also, if you put the fertilizer and they go into the water, the algae will grow faster, and so that they will block the sunlight, and then the plants will die because they don't have enough sunlight, and so then there's a lot of carbon dioxide in the water, so there's no more oxygen in the water, okay? So as the algae die and decay, algae or plants, oxygen is removed. It's replaced with carbon dioxide from the water, leaving insufficient amounts for fish or other organisms such as plants, plankton, any type of water organism to survive. So CQD number 3, give the most important use of ammonia. We use ammonia to produce fertilizers. This is one of the most important. Now, ammonia is used to make ammonium nitrate, NH4NO3, by reacting ammonia with nitric acid. Write a chemical equation. So ammonia, we know it is NH3. It will react with nitric acid, which is HNO3, and then it will produce NH4NO3, and this equation is already balanced. You can try it. It is already balanced. So that is for CQD number 3. CQD number 13. What is an NPK fertilizer? NPK fertilizer is a fertilizer that contains nitrogen or phosphorus or potassium. It can contain like either two of them or one of them, or it can contain all of them. So it has to contain nitrogen and phosphorus and potassium. Now, why do plants need fertilizers? So they can grow and produce more crops, or they can grow faster, in other terms. So that is for part B. Now part C, list one advantage and one disadvantage of using fertilizers. One advantage is that the plants grow faster. So we will say plants grow faster. Why exactly do they grow faster? Because they are supplied with nutrients. Okay, this is an advantage. A disadvantage D is that it will cause, if run off, it will cause algae to grow, and since the algae grows, once algae die, okay, there will be no more oxygen in the water. So this is a disadvantage. So fertilizers will, if they run off, they will cause less oxygen to be in the water. So fertilizers usually contain compounds of nitrogen, phosphorus, and potassium. Nitrogen for green foliage, potassium for healthy growth, and phosphorus for strong roots. So ammonium phosphate, NH4,3PO4, is a fertilizer. Which two elements in ammonium phosphate are important for plant growth? Definitely N and P, because it's an NPK. We use the NPK fertilizer, so it has to have nitrogen and phosphorus or potassium. So here it has nitrogen and phosphorus, or phosphorus, however you like to say it. So that is for part A. Now part B. Why do farmers use fertilizers? Again, many repeated times. It is for plants to grow faster. Okay. Now part C. Many fertilizers contain ammonium sulfate. Ammonium sulfate is made by reacting aqueous ammonia with sulfuric acid. So ammonia is our base, sulfuric acid is our acid. So if there is a reaction between base and acid, they will neutralize each other. So we say this is a neutralization reaction. So that is for part C. Now part D. Aqueous ammonia reacts with nitric acid to make another compound often found in fertilizers. Give the name of the compound produced. Okay, ammonia, NH3, reacts with nitric acid, HNO3, to produce what? NH4. NH4, I don't know why I wrote 3. NO3. And this is called ammonium nitrate. If you don't want to memorize its name, you can say that NH4 is ammonium and NO3 is nitrate. So it is ammonium nitrate. Now E. Give the structure, of ammonia sulfate is shown below. Give the simplest ratio of ammonium sulfate ions in ammonium sulfate. Ammonium and sulfate. So we need ammonium to sulfate. Ammonium is NH4, so let's see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 ammonium compared to how many sulfate 1, 2, 3, 4, 5, 6. So 12 to 6. If you simplify it, they needed the simplest ratio, so then it becomes 2 to 1. So that is part E. Now part F. Ammonium salt react with alkalis meaning bases. Okay, so here bases. Okay, ammonium sulfate plus sodium hydroxide gives us sodium sulfate plus ammonia plus water. Reduce by adding slaked lime to fields which have fertilizers spread on them may result in loss of nitrogen. Now, I don't know if you know this, but slaked lime is CaOH. And CaOH is what? It's an alkali. And if our alkalis will react with ammonium salts, okay, which includes our fertilizers, so our CaOH is our base reacting with our fertilizer, we may lose nitrogen. Why? Because we will form ammonia, NH3. So to put it in simple words, slaked lime is CaOH, okay? If it will react with the ammonium salts, okay, which is in the fertilizers, then definitely it's gonna produce ammonia, which will cause a loss of nitrogen. So when petrol burns in a car engine, pollutant gases are produced. Name 2 gas pollutants. This you should know from last year, I think, or I don't know which year. You should know what is released. Carbon monoxide, CO, and nitrogen monoxide, NO. So please memorize this one. And finally, the very last question. Which of the following fertilizers has the highest percentage yield by mass of sulfur? Just see which one has the biggest amount of sulfur, meaning the biggest amount of S. So definitely by scanning, this has 1S, this has 1S, this also has 1S, and this also has 1S. This has 3S. Why? Because if we spread out the 3, it will be Al2S3O12. So definitely this has the highest percentage by mass of sulfur. So that is it for the nitrogen chapter 6, sorry, the nitrogen topics, topic 6 nitrogen. So I hope you guys enjoyed. Have a wonderful day and good luck on your exams tomorrow.